Hello and welcome back to the lecture on applied econometrics. So today we are going to cover an important topic called multicollinearity. Now when we spoke about the Gauss-Markov assumptions regarding regressions, so we talked about different properties that you need to satisfy. So multicollinearity is one among them. So interesting thing about multicollinearity is that it is not something that we have to ensure that there is no multicollinearity, because there will always be some multicollinearity in a regression equation, but we have to ensure that the degree of multicollinearity is within some limit. Okay, so we'll explain what is multicollinearity and why we are more bothered about the degree as such for multicollinearity. So multicollinearity it arises because of the fact that we have many explanatory variables which might themselves be related, and usually that is the case. So when we talk about any dependent variable, let's say we talk about kids education, right? So when you talk about kids education, there are different explanatory variables. For example, father's education, father's income, right? And there is so many other variables and which are related, right? So for a kid's education, it is very important that usually we'll see that the father's education and kids education are related because a father who is educated, he knows the value of education and he will want his kid to also be educated. So they are correlated. But at the same time, the father needs to have enough income to send his kid to a good school, for example. So all these variables are important, but at the same time, what happens is that father's education and father's income is also related, because father's income was basically a dependent variable of father's education. So this way, all these variables are related, all these explanatory variables are related amongst themselves, and at the same time, they are all explaining the new dependent variable, which is the kid's education. So you take any other example and you will see the complex nature of this reality. So everywhere you will see that all these different explanatory variables which are very which appears to be very directly related to the dependent variable, we will see that the independent variable themselves are related, right? And we will do an example where we will see the number of hours worked by female in the labor force, how they are related to different variables like husband's education, husband's wage, husband's age, the female's parents' education, female's parents' income, females, the number of kids that female has, the number of kids who are below a certain age group, number of kids above certain age group, the tax the family pays, and so forth. And again, if we look at the independent variables, we will see that the independent variables themselves are very highly related. For example, husband's education and husband's income, husband's education and husband's or husband's income and husband's wage, father's education and mother's education, right? And so all the variables that we will see as x variable, there we will see that they are quite clearly they are also related. So that is why, because the reality is so complex, we will see all the explanatory variables, they are actually themselves are related. So multicollinearity is essentially a measurement of how much this sort of relationships are there among the independent variables, among the x variables. So that is what we see in multicollinearity. And if we have multicollinearity, we never say that we are violating Gauss-Markov assumption. We have a problem when we have perfect collinearity, or we have a problem when we have very high multicollinearity. And we are going to see what do we mean by perfect collinearity, what do we mean by imperfect collinearity, what do we mean by high or low multicollinearity. Okay, so let's give a couple of examples. So let's first let me explain what do I mean by perfect and imperfect. Perfect and imperfect collinearity. So when I am dealing with perfect collinearity, so perfect collinearity will normally come from equation like let's say x1 plus let's say 3x2, okay, is equal to let's say 5. Okay, so they are like it's a deterministic relationship. There is no stochastic component here. So every time you basically get, if you want to express x2 in terms of x1, it is going to be 5 minus x1 by 3. Okay, so all the time the relationship is going to be like that. So you don't have any component of randomness. So you always get, for a certain value of x1, you always get a certain value of x2. So this is a case of perfect collinearity. Whereas in case of imperfect collinearity, how we write it as x1 plus 3x2 plus some stochastic component, let's say some error term u is equal to 5. Okay. So, in this case you always have certain error term that will stop the equation from being a deterministic equation, right, and that is why you can run a regression equation. And when you have this sort of equation, you can actually get regression equation, and you can also see the case of, this is a case of imperfect collinearity, and only in case of imperfect collinearity we have this problem of multicollinearity that we see. Imperfect collinearity. So, we will do some examples. We will do some examples to kind of see what is perfect collinearity, what is imperfect collinearity, where multicollinearity may arise, and like some of the cues that we get at this stage we will sort of use when we actually elaborate different examples of multicollinearity. So, let me give you an example. So, when we actually dealt with the concept of dummy variable, let us say when we dealt with the concept of dummy variable, you remember, let us say if there is a dummy variable, let us say gender, and you have two categories, male and female. Okay. Now, we always used one particular category as a reference or base category or base dummy. Other dummy variable, for example, if I use female as a reference or base category, so we used male in the regression equation, and we saw how male is changing with respect to the female. So, that is how we explain a dummy variable. Now, if I include both male and female in the regression equation, so what we will see is that there is your regression equation will actually stop because there is a problem of collinearity. It will give you an error message that there is a problem of collinearity, perfect collinearity. Now, perfect collinearity here in the case of dummy variable comes from the fact that the moment you add, so like if I define this dummy as D, the moment you add all the different values of dummies, so let us say di over all I, so it will always give me a value of 1, because if someone is male, then he is not female, right, or if someone is female, she is not male. But if I represent these dummy with respect using these values 0, 1, let us say female is the base dummy, so I put 0. So, if someone is female, if female is 0, then the person has to be male, so it is 1. And if a person is male, then that person has to be female. If not male, then the person has to be female. And if the person is not male, that person has to be female, and so forth. So, if I add these values, it will always give me a value of 1, because 0 plus 1 is always 1. Now, the problem that we have in case of dummy variable we have seen is that this summation of dummy, which gives me a coefficient of 1, is actually perfectly linearly related with the coefficient of the intercept term. So, intercept term always gives you a value, certain value, but that intercept term could be also be like represented as 1 into certain the coefficients. Okay. So, the value of the variable is a 1 and it has certain coefficient value. So, now because of that, so in case of dummy it has 1 and as a coefficient, and there is a value of as a variable value, the x value, and it has a coefficient value. Now, because both of these variables, so dummy variable and intercept term, both of these has this 1 as the value of the variable, so it will always give rise to a problem of a perfect collinearity. Okay. So, because two variables, they are having the same value, so they are varying in the same manner, so that is why they have a problem of perfect collinearity. So, similarly, if I have the example we have written, so if I use x1 plus 3 x2 is equal to 5, and if I have in my regression, let us say regression equation where I write y x1 y equal to, say, let us say I write it y is equal to beta 1 plus beta 2 x1 plus beta 3 x2. So, if and I can add a u error term. If I run this regression, if I run this regression equation, so what will happen is that because x1 and x2 could be, they are perfectly linearly related, so my regression equation actually drop one of these variables. So, either it will say either it will say error message that it cannot run the regression because x1 and x2 are perfectly linearly related, or it will drop one of these variables if you are using a software like Stata, so it will drop one of these variables, or for that matter R and other softwares also, they are smart enough to do that. So it will drop one of these variables and it will say that it will actually run the regression for you, but there will be a drop of one variables, and that is because of the problem of perfect collinearity. But as such, there is no problem if you have some amount of stochastic component involved, then there is no perfect collinearity and you will have a good regression equation. So then the question of degree of multicollinearity will come if you have the stochastic regression equation. Here we have to kind of see that there are different types. We will do a couple of examples. And one thing we have to remember that when we do not have, there could be relationship and you can basically very defined relationship, but the relationship is not linear. So I'm talking about collinearity, right? So if the relationship is not linear, then you still have the problem of multicollinearity, but you do not have the problem of perfect collinearity. Okay, so let's say if I represent, let's say my x2 is equal to, let's say, log of x1. Okay, so here the relationship is pretty defined, but they're not linear. Okay, so the moment it is not linear, you do not have perfect collinearity problem. You still have the collinearity problem, the multicollinearity problem, but it is not the perfect collinearity problem. Or you can write maybe x3 is equal to, say, x2 square or so forth. So then again it is not a linear relationship. So here again you will not have perfect collinearity problem, but you will have multicollinearity. You will have imperfect collinearity. So that is what we are going to see in next few examples. Okay. So let us do some examples. So let me actually create a small quiz for you, and we'll try to answer the quiz. We'll do an hands-on, and then we'll get back to this and we'll try to answer the quiz. So my first question is that suppose I have my x2, let's say x2 is equal to x1 plus 2, let's say my equation number 1. Then I have, let's say, my x3 is equal to, let's say, 2x2, equation number 2. Then I have, let's say, then I introduce some random variable x4, and let's say my x5 is equal to, let's say, x4 plus x5, all right. Then I have my x6. My x6 is, let's say, I will define x6 as, let's say, log of x5, let's say. So these are like my 4 equations. Now my question to you is, if I run a regression and the regression equation actually takes care of the collinearity, and it actually drops variable if there is a collinearity problem. So how many variables will be dropped in each of this equation if my regression equation is of this form? Let's say I have 2 other variable, let's say x7 and x8, let's say, and for each of this equation my regression equation is like that: y is equal to, let's say, beta 1 plus beta 2 x1 plus beta 3 x2 plus x7 plus x8. So this is one equation, let's say. Then you run another regression equation: y is equal to beta 1 plus, let's say, beta 2 x3 and then beta 3 x2. I'm just taking the variable from all these above equations, and then I add x7, x4, x8. Let's say I have to introduce some other coefficients, so beta 4, beta 5, okay, and you can also add some error term here. So here again I'll add beta 4, beta 5, x8 plus some error term. If I minimize it, let me write a couple of more equations. So y is equal to, in this case, is going to be beta 1 plus beta 2, let's say x5, beta 3 x4, and let's say beta 4 x5 x3. Let's say I use the x3 from here to here. It's x3, all right. So that's going to be beta 4 x3. Just don't, the equations might look a little messy, but it is actually a very simple thing what I am doing. What I am just trying to do is I am basically introducing, in any regression equation I am having these two terms, and I am incorporating all the variables that I am writing in the different equations. Okay. So for every different regression equation I am using different variables from the different equations. And okay, I also have to add in this regression equation, I also have to add, actually I haven't added x7 and x4, but it does not matter really. Let us say we omit x7 and x8, and then the last equation, let us say I write y is equal to minimize the size further, y is equal to, I hope it is still visible, y is equal to beta 1 plus beta 2 x6 plus beta 3 x7 plus 7 or beta 4 x7 beta 5 x8 plus some error term. All right. Now I have all these equations. I have written very long equations. Now let us say I also name them. This is 5, this is 6, this is 7, and this is 8. Now I will let you guess, if I run regression equation for all these different, if I run regression for all these different equations, so how many variables will be dropped? So let us say in the first equation, let us say I will actually try to sort of brainstorm here, and then we will do a hands-on to show you what exactly is happening. So let us look at equation 5, and in equation 5 I have x2 and x1 are there, they have a perfect linear relationship. So they are perfectly collinear, and because of that definitely one variable has to be dropped. So either x2 or x3 will be, x1 or x2 will be dropped, and the regression will run. Okay. So there will be one variable drop in this case. Similarly for equation 2, it is again a perfect linear relationship between x3 and x2. So whenever you run a regression, one variable will get dropped. So it depends, Stata or other softwares can decide which variable it will drop. So it will either x2 or x3 will get dropped. So here again, and one variable will be dropped. So either it is going to be x3 or it is going to be x2 here. Okay, any of this. So essentially this regression equation will show one coefficient for the intercept term and one from either x2 or x3, and then 2 for x7 and x8. So there is no problem with x7, x8 because they are not linearly related with any of this. Now let us see what happens for equation 7. Equation 7, you have x5 and x4 and x3. So they are linearly related, whereas x5 is a sum of x4 and x3. Now here you have like x3 and x4, they are independent, they are not related, or they are not perfectly linearly related, but x5 is. So that is why, because of this dependence, it will drop one of these variables, either x5 or it will drop x3 or x4. So it will again drop one variable in equation 7 here. And finally in equation 8, the last equation, here again I have my x6 and x5. There is a direct relationship, but they are not linear, right? So there is a logarithmic relationship. So here there will be no drop of any of these explanatory variables. So all the explanatory variables will be there because of the fact that my this relationship in equation 4, x6 and x5, they are not linearly related. So that is basically the idea of perfectly linear relationship and imperfect relationship basically. So in case of perfect collinearity, there is a problem, and in case of imperfect collinearity, there is the problem of multicollinearity, and we have to see to what extent we have the multicollinearity problem. All right. Now let us do one hands-on example to sort of get an idea how it is happening. So let me actually open a data set, and I am using the software Stata 14, and I am using a very common sort of problem or common set of equation that we have in macroeconomics, that is Cobb-Douglas production function. Now, we know that in Cobb-Douglas production function, output and labor and capital, they are related, and I have like these linear values for output, labor and capital, and at the same time I have logarithmic value ln output, ln labor and ln capital, and I have included, so for this purpose we just need to remember these variables, we do not need other variables now. And here what I have done is I have included other variables. So, L2 is basically a square of the value for the labor. So, it is a basically L2 is L square, okay. And labor 1, this variable I have created labor. So, I have defined the variable here, labor plus 1 is my labor 1. So, I have just added a value of 1. So, it is again a linear relationship between labor and labor 1. So, labor 1 is equal to labor plus 1, okay. And here I have in labor 2, what I have done is I have basically multiplied labor with 2, okay. So, the value of labor whatever I have multiplied 2 into labor, and this L2 is L square and labor 2 is 2 into labor, okay. So, L2 is a non-linear relationship, it is a square term, and this labor 1 and labor 2, they are linear relationship. So, basically if I write them down, so how this will look like is this. So, the variable L2 is basically labor square, labor 1 is equal to labor plus 1 and labor 2 is equal to 2 into labor. I mean, it might look a little, I mean, just to avoid confusion that we have named it this way, but just to avoid confusion I have written it again. Now, if I run a regression with all these variables, now we have to say using our previous concepts where how many variables my regression, my Stata program will actually drop if I run a regression. And let me, the command is going to be, I actually use a do file here, or I can just simply write the command here. So, if I write, the command is regress, and let us say my regression I am doing ln output on log of output with ln labor, ln capital, just labor, just capital, then I am using L2 which is square of the labor value, and then labor 1 which is a labor plus 1 and labor 2 which is labor into 2. Now, in this equation, before I actually run the regression, I will ask you to guess how many of the variable or how many of the explanatory variables will get dropped. So, based on the previous concepts, so L2 is a square, labor square, so it will not get dropped, it is fine, this one there is no problem. Here it is a problem because it is a linear relationship and perfect linear relationship, and similarly this one also it is a perfect linear relationship, right. So, basically if I run the regression, there has to be a 2 variable drop. So, 2 variables have to be dropped, okay, and if we run it, you will see that actually there are 2 variables Stata has decided to drop. So, it could have dropped either out of these 3, labor 1 and labor 2, it will drop 2 variables out of these 3 variables. So, Stata has chosen to drop labor and labor 1. Now, if you again sort of change the, okay, let me actually again rewrite the code. If I just change the variables a little bit, like if I let us say if I omit say labor 2, so how many variables will be dropped here? So, now the collinearity, the problem is only between labor and labor 1, right. The L square, labor square has no problem because it is not a linear relationship, okay, though it is a direct relationship, but it is not a linear relationship. So, here there will be 1 variable drop, okay. So, we will see that Stata has decided to drop labor 1, all right. So, this is how we basically try to understand from the, if Stata is omitting variables. So, we will see that there are the problem of perfect collinearity, okay. And of course, we have seen in the case of dummy variable, I am not repeating here, how we can actually see if you have all the dummy categories included, we will see that straight I will decide to drop one of this variable because of the perfect collinearity problem. So that's about the perfect collinearity. And when you talk about imperfect collinearity, so basically most of the cases we will see imperfect collinearity. And again I said, like in imperfect collinearity there are multicollinearity problem which is matter of a degree. So there are always some sort of imperfect collinearity and there is always some sort of multicollinearity because of that. But that so we will actually be concerned if the multicollinearity is more than certain extent, all right. So the last part of this, let me actually show you. When you try to understand the problem of multicollinearity, what you do is, another way to actually understand is that you can simply plot scatter plot. Yeah, capital, and we will see. So it is always a good idea to actually see what sort of relationships are there among the variables. It is, of course, it will be quite highly related because it is a log of capital in the y-axis. So they definitely there will be a very definite sort of relationship. So when you try to understand the problem of multicollinearity, what you do is you actually plot all these different variables, all these different x variables, and see how they are related. And if you see some sort of good relationship, like a very discernible pattern, so then you can claim that okay, there are some sort of multicollinearity which might be present. So this is another way to understand if there are multicollinearity. Now I'll end the lecture here, the introduction of multicollinearity, and we'll see what are the implications of multicollinearity on the regression coefficient, on the R square term, and so forth in the next few lectures. Thank you.